the 10 cosmic laws that govern everything. Hello everyone, welcome to my channel. From the tiniest quantum ripples to the most massive clusters of galaxies, from the workings of atoms to the rotation of galaxies, every detail is so perfect. What's even more amazing is that these seemingly cold laws of the universe weave a miracle. It's as if there is a mysterious force that quietly plucks every string of the universe behind the scenes, weaving chaos into harmony. This is by no means an accidental coincidence, but a masterpiece of the laws of nature. Today, we will go together to reveal the 10 iron laws behind the operation of the universe. 1. Uncertainty principle. When it comes to the uncertainty principle, it's one of the most interesting and gripping concepts in physics. When Heisenberg proposed it in 1927, it literally turned people's perception of the world upside down at the time. Think about it. We always used to think that if the tools were advanced enough and the technology was awesome enough, we could know everything about anything. For example, where a particle is and how fast it's moving. That sounds reasonable, right? But Heisenberg threw cold water on it. No, it can't be done. You want to know both the position of a particle and its momentum, that's velocity times mass. Sorry, no way. Why not? The reason is both simple and complex. Simply put, it has to do with the way we measure. Suppose you're looking for a fast-flying bee in a completely dark room. In order to know where it is, you have to shine a flashlight at it, right? But as soon as you shine the flashlight, the photons hit the bee, pushing it farther away or changing its speed. So while you're measuring its position, you're also changing its momentum. This is especially bad in the microscopic world. Because a microparticle is just so small, the fact that you're looking at it with light, electrons, or any other way affects its state. It's as if you're just trying to get a good look at a bubble, and when you touch it, it deforms. You might be thinking, that doesn't sound like it has anything to do with me at all, does it? Actually, it doesn't. The uncertainty principle reveals a deeper truth. There is a certain ambiguity in the world itself. We don't live in a completely deterministic universe, but rather a place full of probabilities and possibilities. As an example, the workings of a quantum computer are closely related to this. Ordinary computers are binary-based, meaning that a bit is either a 0 or a 1. But quantum computers utilize quantum superposition states, where a quantum bit can be both a 0 and a 1. Simply put, a quantum superposition state is like a cat in a box that is both open and closed. This is the Schrödinger's cat experiment. In a superposition state, quantum bits can represent a combination of states, rather than a fixed one. For example, suppose you need to solve a supercomplex cipher, where an ordinary computer would need to try every possible combination one by one. It's like you're looking for someone in a building floor by floor until you find the right one. A quantum computer, on the other hand, can use superposition states to try multiple combinations at the same time, as if it could enter all the rooms at the same time and find the target instantly. Combined with quantum entanglement, a quantum computer can also maintain a mysterious connection between multiple quantum bits, even if they are far apart. This feature allows quantum computers to be far more efficient than conventional computers in solving certain problems, such as factorization and search algorithms. Because of this ambiguity, instead of processing a task step-by-step linearly, quantum computers utilize this ability to exist in multiple states at once to solve problems at an astonishing speed. However, there are limitations to this ability. Quantum computers are still in the research phase and are limited by error correction and stability issues, but they have already shown the potential to change the future. Then again, GPS navigation also indirectly relies on these strange laws of quantum mechanics. This is because the atomic clocks on the satellites have to be very accurate, and these accuracies need to take into account quantum effects. Let me tell you an experimental story. Scientists let electrons pass through two very narrow slits and wanted to see if they passed through one slit like a particle or if they passed through two slits and interfered like a wave. The result: if someone was watching, the electrons behaved like particles. If no one was watching, they behaved like waves. It's as if the electrons know if they're being peeked at. The physicist Feynman once said that this experiment contains the whole puzzle of quantum mechanics. In other words, this phenomenon cannot be explained by common sense unless you accept that uncertainty is the norm in the microcosm. Having said that, I have to mention Nobel Prize winner Richard Feynman. He once joked, "If you think quantum mechanics is easy to understand, you don't understand it at all." This statement has been held as truth by countless physicists because quantum mechanics, and especially the uncertainty principle, is indeed counterintuitive. But on the flip side, it also shows us another side of the universe. The British physicist Brian Cox has written a book called The Quantum Universe. In his book, he says that the uncertainty principle makes us realize that the universe doesn't run like a machine, but is more like a poem, full of surprises and possibilities. So what can we do? We are not actually powerless in the face of this fuzzy world. Scientists have learned to capitalize on this uncertainty by creating many remarkable technologies. Quantum encryption, for example, bases its security on the uncertainty principle. If someone tries to eavesdrop on a message, the observation itself exposes him. At the heart of quantum encryption lies the fragility of quantum states. Imagine an encrypted line of communication between you and a friend. Each piece of information, say 1 bit, is transmitted as a quantum state. If someone tries to sneak a peek, your message will change as a result of the measurement. This change is unavoidable because the uncertainty principle tells us that the measurement itself breaks the original state. A classic example is the BB84 protocol, a method of quantum key distribution. You share a quantum key between you and a friend, and each time you send a quantum bit, the other person receives it and verifies that there is no anomaly. If someone eavesdrops in the middle of the process, the eavesdropper's measurements cause the receiver to notice the inconsistency and learn that the communication has been attacked. This mechanism allows quantum encryption to be considered unbreakable because any eavesdropping would expose itself. It is already being used in high-security scenarios such as banking transactions, military communications, and even satellite transmissions. Although the current quantum network is still immature, it opens a whole new door for information security. Even further, some scientists have suggested that the future quantum internet may rely entirely on quantum entanglement and the uncertainty principle. Such a network would not only be more efficient, but also completely resistant to traditional hacking. So, the uncertainty principle is not a failure or a limitation. It is a natural rule of the game, the order of the microcosm. Although it may sound dangly, this ambiguity is in fact what makes our universe so interesting and full of possibilities. Wouldn't it be boring if everything was certain? 2 Mass and energy equivalence. Speaking of mass and energy equivalence, you've heard the super famous formula, energy, E equals mass, m, times the speed of light, c squared. This is one of the byproducts of Einstein's general theory of relativity. Even though it's as short as a text message, it carries a lot of weight. Let's get right to the point. Why are mass and energy equivalent? What does this formula really mean? Let's start with the formula itself. E is energy, m is mass, and c is the speed of light. The speed of light is a very large number, about 3 times 10 to the 8th power of meters per second. So even a very small mass multiplied by the square of the speed of light can produce a huge amount of energy. That might be a bit abstract, so let's put it another way. Imagine you have a piece of chocolate in your hand. If you follow this formula and convert all the mass of the chocolate into energy, it releases enough energy to keep a city's light bulbs on for days. Einstein didn't write this formula as an inspired doodle, he derived it while thinking about the relationship between light and matter at the end of the 19th century. The scientific community's understanding of light and energy was stuck in the framework of classical physics. Einstein proposed that photons had energy and momentum, which implied that there was some connection between mass and energy. Interestingly, this formula did not appear in the title of Einstein's 1905 paper. At the time, his focus was on exploring the nature of light, and this formula was just one of the inferences. It wasn't until later that people realized the importance of this formula. The most direct manifestation of the equivalence of mass and energy is nuclear energy. In a nuclear reaction, a small amount of mass is converted into a huge amount of energy. Let's talk about the example of the atomic bomb. During World War II, the Manhattan Project in the United States used the principle of E equals mc squared to develop powerful nuclear weapons. Take the little boy atomic bomb dropped on Hiroshima as an example. The core of the bomb was uranium-235, and in the process of nuclear fission, part of the mass of the uranium was converted into energy. The loss of a few grams of mass is enough to destroy a city. Of course, nuclear energy is not only used to make weapons. Nuclear power plants are a version of E equals mc squared for peaceful applications. In a nuclear power plant, the energy produced by nuclear fission is used to generate electricity for our lives. If nuclear energy seems too remote, we can look at more everyday examples. For example, the technique of positron emission tomography, PET, in medicine utilizes the transformation of mass and energy. A radioactive isotope injected into a patient releases positrons, which meet electrons and undergo an annihilation reaction, converting their mass into photon energy. These photons are captured by an instrument that creates a detailed image of the body. One might ask, why is mass multiplied by the square of the speed of light? What is the relationship between the speed of light and mass? This question goes back to the core idea of relativity. Space and time are one and the same. The speed of light, c, is more than just the speed at which light travels in physics. It represents the speed limit of nature. Einstein's theory tells us that any object approaching the speed of light experiences strange phenomena, such as time slowing down and length contraction. And the mass itself increases. So, the square of the speed of light is not randomly placed in the formula. It is derived from the space-time relationship and the kinetic energy formula. Speaking of experiments, particle gas pedals are the best proof of this formula. In the Large Hadron Collider (LHC) at the European Centre for Nuclear Research (CERN), scientists make particles collide at speeds close to the speed of light. With each collision, new particles are created. The total energy of these particles matches exactly the mass initially put into them. This live demonstration of mass-energy conversion is a classic illustration of this equation. Another cool example is stellar fusion. Every day, the Sun converts some of its mass into light and heat by fusing hydrogen nuclei into helium atoms. This is why we can feel the warmth of the Sun. Let's talk about the process of nuclear fusion in more detail. The Sun's core is at a temperature of about 15 million degrees Celsius, and the pressure is so great that the conditions are extreme enough for hydrogen nuclei to overcome the electrostatic repulsion between them and undergo fusion. In fusion, 4 hydrogen nuclei, protons, combine to form a single helium nucleus while releasing enormous amounts of energy. This is because the mass of the helium nucleus is slightly smaller than the total mass of the 4 hydrogen nuclei, and that missing mass is converted into energy, calculated as E equals mc squared. This may sound a bit abstract, but to put it in a more graphic way, imagine that the Sun is a cosmic energy factory, where hydrogen is fed into a reactor every day as raw material to produce light and heat. Scientists estimate that every second, the Sun will consume about 600 million tons of hydrogen, of which about 4 million tons of mass directly into energy, and that energy travels across the vastness of space in the form of photons, eventually reaching Earth and providing the conditions for life on Earth to survive. The next time you bask in the Sun, think about this. Every ounce of warmth you feel actually comes from that spectacular nuclear fusion reaction inside the Sun. Why is nuclear fusion so efficient? Nuclear fusion is one of the most efficient ways of releasing energy known. Unlike nuclear fission, nuclear fusion releases more energy and does not produce long-lived radioactive waste. This is why scientists have been working hard on fusion energy in the hope of one day realizing an artificial mini-sun in human society. The International Thermonuclear Experimental Reactor (ITER) is currently the largest fusion research project. Its goal is to mimic the nuclear fusion process of the Sun, utilizing the isotopes of hydrogen, deuterium, and tritium, to achieve sustained energy output in the laboratory. If successful, fusion will provide humanity with a virtually unlimited supply of clean energy. The concept of mass and energy equivalence is not just a breakthrough in physics, it also changes our understanding of the nature of the universe. Matter and energy are no longer two separate things, but can be transformed into each other. This made us realize that the universe is a highly unified system. Philosopher of science Carl Sagan once said, "We are all stardust." This statement actually has E equals mc squared behind it. The matter in the universe is condensed from energy. In other words, you and I are essentially a collection of energy. 3. The law of cause and effect. Have you ever wondered why things are always cause and effect? For example, if you slip on a banana peel, this slip effect is obviously due to the fact that you stepped on the banana peel, cause. This kind of cause and effect relationship sounds very natural. After all, we have been living in this logic since childhood. But in fact, the law of cause and effect is not taken for granted, and there are many interesting scientific questions behind it, especially when we put it into the context of relativity and quantum mechanics. What is the law of cause and effect? Simply put, the law of causality means that the cause comes before the effect. If event B is the result of event A, then it must occur before B. This law seems to be unquestionable in our daily lives, but on the scale of the universe, its boundaries and implications are not so simple. Einstein's theory of relativity tells us that the causal relationship between events is limited by the speed of light. That is, information cannot travel faster than the speed of light, which ensures that causality is not reversed. Suppose there is a person standing on Earth and another person standing on Mars. If the person on Earth pushes a button that causes an explosion on Mars, the causality will take time to pass, at least until the speed of light passes the information. So, in any case, the explosion on Mars would not have happened before the button was pressed. In general relativity, events are categorized into three types: time-like, space-like, and light-like. Time-like events, events that occur on the same timeline with a clear cause and effect relationship, such as when you cough after drinking water. Space-like events, two events that are so far apart that even light takes a long time to travel past, such as two events on Earth and a distant galaxy. Light-like events, events that can be connected at the speed of light, such as a star emitting light that is seen by us. General relativity states that only time-like or light-like events can be causally connected. Space-like events cannot be causally connected. This distinction effectively avoids the paradox of effect before cause, and allows the law of cause and effect to remain consistent in the macroscopic world. With regard to the law of causality, science fiction movies are an area that particularly likes to challenge it. For example, many time travel stories involve paradoxes of the law of cause and effect. The classic example is the movie Back to the Future. In the movie, the hero Marty goes back in time and almost prevents his parents from meeting by accident. If they hadn't met, then Marty would never have been born, but if he wasn't born, how could he go back in time? This type of grandfather paradox is a classic challenge to the law of cause and effect. The effect influences the cause, and the whole chain of cause and effect is thus caught in a dead end. Scientists love them and hate them, they're brain-burning, but they also make us think more deeply about the nature of the law of cause and effect. Einstein's theory of general relativity is one of the cornerstones of modern physics. Not only does it tell us how time and space are curved, it also provides cosmic protection for the law of cause and effect. If the law of cause and effect were broken, the basic rules of the universe would be thrown into chaos. The most obvious problem is that we cannot predict the future or explain the past. For example, if a particle can influence the results of a measurement before it is taken, then all physics experiments lose their reliability and science would be meaningless. A deeper effect is that the universe could become disordered. For example, the gravitational trajectory of a planet around a star could be disrupted by a reversal of the law of cause and effect, leading to the disintegration of entire galaxies. Einstein's relativistic model avoids this scenario by constraining the structure of spacetime, protecting the stability of the universe. Although general relativity protects the law of causality, its equations also predict certain phenomena that may challenge the law of causality, such as the closed time-like curve, CTC. The closed time-like curve is a specialized spacetime structure in which a particle can go back in time and even meet its past self. This phenomenon could theoretically occur under extreme conditions, such as near a rotating black hole, Kerr black hole, or in a wormhole environment. If you were to enter such a region in a spaceship, you could theoretically go back in time and even change history. But scientists believe that there is some mechanism in the universe that would prevent such a thing from happening. Stephen Hawking has developed the chronology protection conjecture, which argues that any condition that could trigger the collapse of the law of cause and effect would be prevented by natural laws, such as the possibility that wormholes could collapse before they form. Even under the most extreme conditions in the universe, the law of causality is still guarded. For example, although a black hole is a place where spacetime is extremely curved, its event horizon, a boundary from which no light can escape, prevents information from leaking from the inside to the outside. In other words, any causality inside the black hole does not affect the universe outside, which is equivalent to creating a quarantine for the law of causality. Another example is the propagation of gravitational waves, which were first detected by the LIGO team in 2015 as ripples in spacetime created by the collision of two black holes. These gravitational waves propagate at the speed of light, ensuring that the message of gravity does not transcend the limits of the law of causality. If relativity protects the macroscopic structure of the law of causality, quantum mechanics allows us to start rethinking the meaning of the law of causality in the microcosm. In the quantum realm, things get a little weird. For example, there is a famous experiment called the quantum delayed choice experiment. The experiment was designed by physicist John Wheeler to see if an observer's decision could influence the outcome of an event against the clock. In the experiment, a photon seemed to know how you would choose to observe it, thus changing its past behavior. This phenomenon makes it seem as if cause and effect are backwards, but scientists explain that this is not a reversal of the traditional law of cause and effect, but rather a non-classical feature of quantum mechanics. Despite its philosophical and scientific challenges, the law of cause and effect remains an indispensable foundation for technology and scientific experimentation. For example, in drug development, the law of causality is used to determine whether a drug is actually effective against a particular disease. Scientists infer a cause and effect relationship between a drug and its therapeutic effects by comparing the results of a test group with those of a control group. Without the law of causality, such experiments would simply not be valid. Causal inference is also becoming increasingly important in the field of artificial intelligence. Modern AI models often rely on large amounts of data, but causal inference tries to help machines understand the causal relationships behind the data, rather than simply recognizing patterns. In this way, AI can better predict and respond to complex situations, such as medical diagnoses or economic forecasts. From a philosophical perspective, the law of cause and effect has been a central topic of discussion as far back as the ancient Greek period. Aristotle proposed a four-cause theory of causality: material, formal, motivational, and purposive causes, which laid the foundation for later Western philosophical understanding of causality. Modern philosophers, on the other hand, have tried to explore at a more fundamental level whether the law of causality is a fundamental property of the universe or merely a tool used by the human brain to make sense of the world. Some have even suggested that causality may simply be our subjective interpretation of random events after all. Randomness and chance are very common in the quantum world. While the law of causality may seem ubiquitous, it may fail under certain extreme conditions in the universe. For example, inside the event horizon of a black hole, causality may be completely reversed due to the violent curvature of spacetime. Stephen Hawking has proposed an information paradox to explore whether black holes could violate the law of causality and make information disappear completely. Although there are some theories, such as the holographic principle, that try to solve this problem, we still cannot fully understand how causality behaves in these extreme environments. 4. Symmetry and brokenness. Have you ever noticed that many things in life seem to be perfectly symmetrical, but when you look closely, there are always some small imperfections? For example, a round apple is very close to symmetry no matter which way you look at it, but there is always a place where the tip of the apple is, which destroys that perfection. This broken symmetry phenomenon actually applies to the universe, and is very significant. It explains why the particles in the universe have mass, and why our world is the way it is. What is symmetry? Symmetry is actually quite easy to understand. You can imagine a mirror. If something is symmetrical from side to side, like a heart-shaped chocolate, its reflection in the mirror will look exactly like the body. Symmetry in physics says that if you look at things differently, or with a different frame of reference, certain laws should remain the same. For example, if the Earth goes around the Sun, the shape of the Earth's orbit is still an ellipse whether we are standing at the South Pole or the North Pole. This is the rotational symmetry of the laws of physics. Symmetries in the universe are much more complex than this, such as the unification of the electromagnetic and weak nuclear forces, which were initially symmetrical but were broken in the early universe. We deal with broken symmetries every day. For example, if you stand a pencil on a table, in theory it should be perfectly symmetrical and upright, but in reality it will always fall in a certain direction. This direction of fall is the result of symmetry breaking. In physics, there is a phenomenon called spontaneous symmetry breaking, which means that the basic rule of the system is symmetry, but the actual situation has chosen a direction. This is how the particle mass of the universe came to be. In the instant after the Big Bang, all elementary particles had no mass and were free to travel at the speed of light. But as the temperature of the universe dropped, the Higgs field kicked in. You can think of the Higgs field as an invisible ocean, and as particles move through it, they are resisted like a human swimmer, and this resistance is what we perceive as mass. There is an interesting true story about the Higgs field and symmetry breaking. In 2012, CERN announced the discovery of the Higgs boson, which is known as the God particle, and is the key to verifying the existence of the Higgs field. The discovery was dramatic. The experiment was like searching for a needle in a giant meadow, and the team analyzed data from tens of billions of particle collisions before finally finding a hint of proof of the Higgs boson's existence. The Nobel Prize in Physics was thus awarded to Peter Higgs and François Englert. CERN scientists explained the Higgs field with a vivid analogy. Imagine a room full of people, and if a celebrity walks in, people will gather around, and the celebrity will move slower. The slowing down of the celebrity is similar to a particle gaining mass. When it comes to symmetry breaking, the classic example is the separation of the electroweak force. In the early days of the universe, When temperatures were extremely high, the electromagnetic force and the electroweak force were indistinguishable. They behaved as if they were one and the same force. But when the universe cooled down to about a certain temperature, this symmetry was broken, and the electromagnetic and electroweak forces went their separate ways. This separation not only explains why particles have mass, but also shapes our universe today. If the symmetry hadn't been broken, electrons or protons might not exist at all, let alone atoms and life. Physicists often use the analogy of an ink drop to describe symmetry breaking. Imagine a perfectly symmetrical, round ink drop on a piece of paper. Over time, it spreads in different directions, eventually forming random, asymmetrical patterns. There is also an experiment called the liquid helium superfluid vortex. When liquid helium cools to near absolute zero, it becomes a strange state, superfluid. In this state, the motion of the liquid helium exhibits a perfect symmetry, but when subjected to small perturbations, such as the shape of the container, the flow of the liquid helium creates small vortices, a classic physical demonstration of symmetry breaking. There is also a higher-order symmetry in the universe called CPT symmetry, which refers to the combination of time reversal, T, space flipping, P, and particle-antiparticle transitions, C. In theory, the laws of physics should remain consistent no matter how you flip, mirror, or invert time. But experiments have found that this symmetry can also be broken, such as when neutrinos and antineutrinos behave slightly differently. This breaking could be an important reason why the universe is dominated by matter, rather than being made up of equal amounts of matter and antimatter. Imagine what the universe would look like if the symmetry had never been broken, or if it had been broken in a slightly different way. If electroweak symmetry had not been broken, the Higgs field did not exist, and particles would not have mass. Then all the matter we see today might not have formed at all. If CPT symmetry had held perfectly, matter and antimatter would have annihilated each other after the Big Bang, and the universe might have been empty. Some scientists believe that this subtle breaking process may be one of the proofs of the multiverse theory. Out of the countless parallel universes, only a very few of them have the physical properties that we know. Finally, let's go back from the universe to humanity itself. Symmetry and brokenness actually shape all aspects of life. The human body appears to be symmetrical, but the distribution of internal organs is asymmetrical. Our DNA molecule is a natural broken symmetry. Perhaps broken symmetry is not only an iron law of the universe, but also a philosophical implication. A perfectly symmetrical world may not be interesting, and the real beauty is often hidden in those subtle asymmetries. 5. The principle of the centerless universe. Have you ever fantasized as a child what the center of the universe would look like? Would it be a shiny place, or like in the movies, a huge black hole that sucks everything in? Actually, yeah, scientists have told us, the universe doesn't have a center at all. That sounds a bit counterintuitive, doesn't it? After all, we're used to the idea of a center. The Earth has an equator, our solar system has a sun, and even every town has a city center. But the universe breaks this rule. It has no center and no edges. This is part of what is known as the principle of the centerless universe, or more formally, the cosmological principle. The cosmological principle is one of the cornerstones of modern cosmology, and it says that when you look at the universe from any point in the universe looks the same on a large scale. You can think of it as a huge, uniform cake. No matter which piece of the cake you stand on, you see a similar distribution of sunken raisins. This uniformity and isotropy, which does not depend on direction, allows us to describe the entire universe in a mathematical model. This brings us to the cosmic microwave background, CMB, which is known as the afterglow of the Big Bang. In 1964, two American scientists, Arno Penzias and Robert Wilson, discovered the CMB by chance. They were observing with an antenna and realized that no matter where the antenna was pointed, there was always a background noise. At first they thought it was bird droppings, but after cleaning it up the noise was still there. They realized that what they were capturing was the echo of the birth of the universe. This background radiation is almost perfectly isotropic, with temperature differences on the order of -10 to the 5th power, no matter which way you look at it. This proves that the universe is indeed homogeneous on large scales, and that no one direction appears to be more special. Why does the universe have no center? To understand this, we have to start with the Big Bang. Many people mistakenly think that the Big Bang was the explosion at some point that created everything. But in reality, the Big Bang was not an explosion at a specific location, but an expansion of the entire space itself. You can imagine the process of blowing up a balloon. The distance between each point on the surface of the balloon increases as the balloon expands, but the surface of the balloon itself has no center, at least from a two-dimensional perspective. We live in a three-dimensional universe, and the situation is similar. The expansion occurs throughout the entire cosmic space, rather than spreading outward from a single point. This concept of centerlessness is always maddening, because our brains are used to seeing the world from a geocentric perspective. So one might ask 1. Since the universe is centerless, are we the center when we look at it from the Earth? Nope. This is an illusion. No matter what planet you are standing on, the universe will look like it is centered on you. This is not because the Earth is special, but because the expansion of the universe is uniform. 2. If the universe is expanding, where is it expanding to? This question is also very common. The universe is not expanding into some space, but space itself is expanding. Like the surface of a balloon, the distance between points is increasing, but the balloon is not expanding into some larger container. So is it possible that the universe has a boundary? This is an interesting question. The prevailing view among scientists is that the universe may be a finite space without boundaries. What does this mean? For example, the surface of the Earth is finite. You can run circles around it and never fall off the edge. But it doesn't have a boundary, so you don't suddenly come across a wall that says, "End of the world." Some cosmological models suggest that the structure of the universe may be similar. If the curvature of the universe is positive, e.g., the surface of a four-dimensional sphere, then it is finite, but you wouldn't encounter a boundary if you walked through it. To be honest, the concept of a centerless universe has a big impact on the philosophical outlook of human beings. In ancient times, it was widely believed that the Earth was the center of the universe. Later, Copernicus proposed the heliocentric theory, and the centrality of human beings was shaken for the first time. Later, we found that the solar system is only a corner of the edge of the Milky Way, and the Milky Way is only one of the countless galaxies in the universe. The centerlessness of the universe further tells us that there may be nothing special about humans. Where we are is just an ordinary node in the giant web of the universe. This realization is both humbling and awe-inspiring. Regarding experiments on the centerlessness of the universe, Stephen Hawking once proposed a brainstorm. If we lived in a giant cosmic simulator, would we be able to detect the center of the simulation? He thought that if such a center existed, very energetic particles, such as cosmic rays, might show some kind of bias. But no such bias has been detected so far, which again supports the idea that the universe is centerless. The principle of the centerless universe is like a declaration of the universe. No point is more special than any other point. In this seemingly random and deeply regulated universe, each of us may be the center of his or her own being, and at the same time a part of the whole. Because of this, understanding this iron law not only expands our scientific knowledge, but also allows us to reflect on a philosophical level. How do we find our place in a centerless universe? 6. 4 fundamental forces interacting with each other. When it comes to the iron laws of the universe, we have to mention the 4 ubiquitous fundamental forces. Just as we can't live without water, electricity, and internet, these 4 forces are the basis of the universe's operation. These 4 guys are gravity, electromagnetism, strong interaction, and weak interaction. Let's start with gravity, which is the force we are most familiar with. Whenever you jump up and fall down, that's gravity reminding you of its existence. In fact, the essence of gravity is the attraction between masses. The greater the mass, the stronger the gravitational force. Gravity is a chronic force that controls the macrostructure of the universe. The formation of galaxies, planets orbiting stars, and black holes devouring matter are all orchestrated by gravity behind the scenes. Newton and Einstein can be considered the 2 faces of gravity. Newton discovered the law of gravity, but Einstein took it a step further and told us that gravity is actually the result of the bending of space-time. Doesn't that sound particularly incredible? But that's the beauty of science. Next we talk about the electromagnetic force. This is a force you use every day, but probably don't realize it. The electromagnetic force governs the interactions between molecules and atoms. The electromagnetic force is responsible for the way you use your cell phone, blow-dry your hair, turn on a light, and even the touch you feel when you touch something. Without it, atoms wouldn't be able to hold together, and wouldn't the world just fall apart? One of the wonderful properties of electromagnetism is that it is much stronger than gravity. For example, you can pick up a paperclip with a small magnet, and the electromagnetic force exerted by the small magnet will have overcome the gravitational force of the Earth on the paperclip. In addition, the electromagnetic force has a positive and negative two character. Positive charge suck negative charge. The story of opposites attract probably comes from here. Strong interaction force. This is the strongest of the four basic forces. The name is also a domineering. The strong force is mainly responsible for keeping the protons and neutrons in the nucleus of an atom tightly tethered together. You know, protons are positively charged, so they should be mutually exclusive, but the strong force pressed them together. Without the strong force, atomic nuclei would have disintegrated long ago and our world would not exist. Scientists even say that the strong interaction force is the glue of the universe, without which there would be no us. But the strong force also has its own little temperament. Its range of action is very short, roughly the size of an atomic nucleus. So you won't feel any direct impact in your daily life. However, the power of nuclear energy and nuclear weapons comes from the huge amount of energy released when the strong force is in action. The theater of the weak force is the world of subatomic particles. Its effects are short-lived but significant. For example, the weak force is crucial in beta decay, the process by which a neutron inside the nucleus of an atom turns into a proton, or vice versa, releasing an electron or positron, as well as a neutrino. This decay phenomenon has not only allowed scientists to understand the dynamics inside the nucleus, but has also helped explain the formation of elements in the universe. The source of the sun's energy is also inseparable from the weak force. Nuclear fusion inside the sun is a multi-stage process, and one of the key steps is the reaction of converting protons into neutrons, which is the work of the weak force. Without this step, hydrogen atoms could not be converted to helium, and there would be no sunlight or heat as we are familiar with. Another fascinating feature of the weak force is that it leads to a chiral preference for particles. Simply put, particles in weak interactions are biased to choose a particular direction of rotation. This preference breaks certain symmetry rules in physics, such as conservation of utopia. This discovery has shocked the scientific community and provided new clues for studying the deeper laws of particle physics. In addition, neutrino research is closely related to the weak force. Neutrinos are particles of very small mass that hardly interact with other matter and have been called the ghosts of the universe. The behavior of neutrinos gives scientists a glimpse into the complexity of the weak force. For example, the discovery that neutrinos have mass challenges the Standard Model and suggests that there may be deeper laws of physics waiting to be revealed. Overall, the weak force may seem weak, but it is behind many of the key processes in the universe. From radioactivity to the energy production of stars to the esoteric physics of neutrinos, it has always shaped the universe. It teaches us that what really matters sometimes doesn't need to be very powerful, it just needs to be everywhere and silently driving everything. Interestingly, these four forces are not isolated. Scientists have been trying to unify them. The electromagnetic and weak forces have been unified into the electroweak force, and the Standard Model is at the heart of this theory. As for the more ambitious grand unified theory, or theory of everything, which brings gravity into the picture, it is the holy grail of physics. Some say that if scientists succeed, we will be able to more fully understand the laws of the universe, and may even be able to break through the limitations of existing technology, which is exciting to think about. In short, the four fundamental forces are like the four pillars of the universe, holding up the operation of everything. Whether it is the microscopic world of particles or the macroscopic structure of galaxies, there are shadows behind them. Siebter Fermi-Paradox. The universe is so big that there are hundreds of billions of galaxies, and in each galaxy there are hundreds of billions of stars, and each star may have so many 1 or 2 habitable planets. In theory, there shouldn't be so little intelligent alien life. But we humans have looked up at the stars and spent decades, if not centuries, searching for them, and we still haven't received any clear text messages from aliens. Why is that? This question was first raised by physicist Enrico Fermi. It was 1950, and Fermi was having lunch with some colleagues. Yes, inspiration sometimes pops up at the dinner table, when he casually asked, "Where are they all?" Since then, this simple question has become a great mystery that has scientists scratching their heads to this day. Let's start with simple probabilities. There are almost 400 billion stars in the Milky Way alone, which in turn is just an ordinary galaxy in the universe. If you think of these star systems as a giant cosmic lottery, then the appearance of intelligent life should not be particularly rare, right? Plus, the universe is 13.7 billion years old, so alien civilizations have had plenty of time to develop technology, explore the galaxy, and even visit Earth. But then the question arises, we haven't found them. The scientific community has come up with many possibilities to answer this question. Some sound plausible, others a little crazy. Possibility number 1, we're alone. This hypothesis is straightforward and a bit heartbreaking. Perhaps intelligent life really is a rare existence, and life on our planet is nothing short of a cosmic miracle. Keep in mind how many fortuitous events went into the evolution from single-celled organisms to intelligent beings. For example, the dinosaurs became extinct, and if an asteroid hadn't hit the Earth, mammals might never have had a chance to rise, let alone humans. Some scientists believe that this could be the so-called Great Filter at work. This filter could have occurred at the origin of life or during the development of civilization. In other words, perhaps most planets never developed life in the first place, or if they did, they went extinct at some point due to war, environmental collapse, etc. Our planet escaped these catastrophes. It may have been a lucky accident that our planet escaped these calamities. Possibility number 2, they're too far away. Let's not forget that the universe is unimaginably large in scale. Even if alien civilizations do exist, their home may be too far away. The nearest habitable exoplanet is probably dozens of light years away. If they wanted to send us a hello, it would take decades for a signal to reach Earth. And it's another matter if the signal can get through the noise and interference of the universe. Not to mention the limited level of human technology. In our search for extraterrestrial life, we rely heavily on radio telescopes to listen for electromagnetic signals. But what if instead of electromagnetic waves, the aliens are using communication methods we don't even know about? For example, if they use quantum entanglement to chat directly, then we are talking to a cow. Possibility 3, they deliberately ignore us. This may sound a little hurtful, but maybe aliens are intentionally ignoring us. Think about it, humans on Earth have only been technologically advanced for a few hundred years and are sort of cosmic novices. To advanced civilizations, we may be as interesting as animals in the forest, but there's no need to intrude. A famous analogy is the zoo hypothesis, which means that aliens may be observing us, just as we visit the zoo. But they have their own rules and can't interfere with our development. Or to put it more frighteningly, aliens may be afraid of us. After all, we humans have fought so many wars in our history that our first reaction to something new is often possession and conquest. To a peaceful alien civilization, they might feel that it's safer to stay away from us. Possibility 4, they're already here, we just haven't realized it. This is also a cerebral speculation. Some people believe that aliens may have already visited Earth and are even here now, they're just hiding it too well. Have you ever seen the Men in Black movie? There it says that aliens take on the guise of ordinary humans and blend into our society. Although this sounds like the plot of a science fiction movie, some UFO enthusiasts are convinced of this. There is also the possibility that aliens have left some kind of trace or signal that we simply don't know how to interpret. Just as an ant can't read a mathematical formula written by a human, we may lack the ability to understand an alien civilization. Possibility 5, we're looking in the wrong place. Earthlings are actually very limited in the way we look for alien life. We've mostly focused on the habitable zone, the area where liquid water might exist, but alien life may not need water in the same way we do. Perhaps they live in stellar atmospheres or hide under frozen ocean worlds. Also, we tend to look for electromagnetic wave signals, but perhaps aliens evolved long ago to not use this primitive form of communication. The famous scientist Carl Sagan has mentioned that maybe we need to think outside the box and try to find answers from a whole new perspective. All in all, the Fermi paradox is like a huge question mark hanging in the minds of scientists and ordinary people. It makes us realize that human beings may be really small in the universe and reminds us to stay humble and curious. Perhaps the answer will suddenly be revealed sometime in the future, or we will be spinning our wheels in this puzzle forever. 8. Quantum superposition and entanglement. When it comes to quantum superposition and entanglement, this is definitely a marvelous part of the quantum world. What is quantum superposition? The core idea of quantum superposition is that in the microscopic world, particles can be in more than one state at the same time, rather than being black and white as we usually see. As an example, we often use Schrödinger's cat to illustrate this concept. Suppose there is a cat locked in a box with a quantum switching device. If the switch is activated, it releases poisonous gas and the cat dies. If it is not activated, the cat lives. But before we open the box, quantum mechanics tells us that the cat is both alive and dead at the same time, and that this simultaneous state is a quantum superposition. You may be thinking, that's impossible. How can a cat be alive and dead at the same time? In fact, this is just an analogy. The real superposition is not a cat, but quantum particles, such as electrons or photons. In experiments, scientists do observe this phenomenon, such as the fact that light can take two paths at the same time, which is at the heart of the double-slit experiment. Speaking of the double-slit experiment, the story is really interesting. Imagine you take a handful of marbles and shoot them at a baffle with two slits. You would expect the marbles to go through either the left slit or the right slit, creating two banded patterns on the screen behind you. But if you do this experiment with photons, particles of light, the results are completely different. Instead of obediently choosing a single slit, the photon seems to travel through both slits at the same time, creating an interference pattern on the screen. This means that the photon does not pass through a slit in the classical way, but is in a superposition state, where it takes two paths in a sense. What's even more bizarre is that when scientists tried to use a detector to observe which slit the photon went through, the superposition state instantly disappeared, and the photon became a normal particle. This makes people cannot help but exclaim, "Look, the quantum world is shy." If quantum superposition makes people feel marvelous, then quantum entanglement is the concept of direct people collapse. Entanglement means that two or more particles can be connected in such a way that, even though they are separated by thousands of miles, a change in the state of one particle immediately affects the other. Albert Einstein once called this phenomenon ghostly superluminal action, because it seems to violate the relativistic principle that information cannot travel faster than light. Let's say you and a friend each have a pair of gloves. You go to New York, he goes to London, and the left and right hands of the gloves are randomly assigned. When you open the box in New York and see the left-handed glove, you immediately know that your friend's box contains the right-handed glove. While this example may seem commonplace, quantum entanglement is much crazier than that, because the association of entangled particles transcends any distance limitations, and doesn't even require any signaling. The phenomenon of entanglement is not just a theory. Scientists have verified it experimentally. For example, the Bell experiment proved that the correlation between particles really violates the expectations of classical physics. Another interesting experiment is the cosmic entanglement experiment in 2017, which completely refreshed people's understanding of quantum entanglement. In order to eliminate the problem of artificial selection in the experiment, scientists decided to use photons from distant galaxies as random number generators. The experiment works like this. Light from two galaxies billions of light-years away is used to determine the direction in which the quantum measurement device is set up. This method ensures that the signals determining the measurement setup existed before the formation of the Earth, thus avoiding the possibility of potential a priori correlation or manipulation. The results show that quantum entanglement holds even under such extreme conditions. The significance of this experiment is far-reaching, as it not only further validates the reality of quantum entanglement, but also suggests that such correlations may indeed be one of the fundamental properties of the universe. Scientists have jokingly called the experiment a cosmic endorsement of the entanglement phenomenon. Quantum superposition and entanglement are more than just marvels of physics, they also raise deep philosophical questions. For example, if particles can be in more than one state at a time, what is our reality? Or is the reality we see just one of many possibilities? Quantum phenomena are also often used in science fiction to build storylines, such as the concept of parallel universes. According to the many worlds interpretation of quantum mechanics, each time a superposition state collapses, the universe splits into different versions, each corresponding to a possibility. Sounds like an episode of Black Mirror or The Revenant, doesn't it? Anyway, quantum superposition and entanglement make us rethink the nature of the world. From seemingly absurd experimental phenomena to highly promising technological applications, these quantum phenomena are revolutionizing our understanding of reality. The next time you hear about quantum mechanics, I hope you won't just be confused, but you'll appreciate the wonders and possibilities behind it. It is truly a universe that is stranger than fiction. 9. Critical density of the universe. Have you ever wondered what the future of the universe will be like? Will the stars slowly go out, the galaxies scatter, and eventually the whole universe will be plunged into endless darkness? Or on the contrary, will it be like a stretched rubber band that expands to its limit and then suddenly collapses, squeezing everything into an infinitesimal point? In fact, the answer to these questions is hidden in a key value, the critical density of the universe. Simply put, the critical density is a dividing line that determines the future fate of the universe. You can think of it as the balance of destiny of the universe. If the total density of the universe, that is, the average density of all the matter and energy in it, is exactly equal to this critical value, then the expansion of the universe will gradually slow down, but it will never completely stop. What if the density is greater than the critical value? It's like a spring that's been pressed too far, and when it expands to a certain point, it bounces back, and the universe starts to contract, and eventually it may fall into a big crunch. What if the density is less than the critical value? The situation is completely different. The universe would keep expanding faster and faster, and could eventually become a cold, thin, dead universe. Where are we now? Current observations, such as those from the Planck satellites and other cosmological programs, suggest that the density of the universe is very close to a critical value. This sounds like a cosmic coincidence, as a slight deviation could lead to a completely different result. Scientists speculate that it may be related to dark energy, a mysterious form of energy that drives the accelerated expansion of the universe. Dark energy is like an invisible pusher that makes the universe expand faster and faster. To put it another way, if the universe is an expanding balloon, dark energy is the force that keeps blowing air into the balloon. But this blowing is very strange. Dark energy is not evenly distributed, but becomes stronger and stronger as space expands. This leads to an amazing phenomenon. The farthest galaxies in the universe are moving away from us faster than the speed of light. Of course, this does not violate Einstein's theory of relativity, because it is space-time itself that is expanding, not objects moving through space. Scientists have calculated that the critical density of the universe is about 5 times 10⁻27 kilograms per cubic meter. How small is this number? In other words, the total amount of matter at the critical density in a 1-meter square box doesn't weigh as much as a grain of dust. Even so, this minuscule value is relevant to the fate of the universe. Scientists first came up with the concept based on studies of general relativity and Hubble's law. In the 1930s, Edwin Hubble observed galaxies and realized that they were moving away from each other at a rate proportional to their distance, which meant that the universe was expanding. And in the late 20th century, the concept of critical density became clearer with the observation of the cosmic microwave background radiation and the mapping of large-scale galaxy distributions. The real breakthrough came with an unexpected discovery in 1998. Scientists had thought that the expansion of the universe should be gradually slowing down, but observations showed that it was instead speeding up. This discovery made dark energy a key factor in explaining the fate of the universe. When it comes to the future of the universe, many people will wonder, what will happen to the stars? In fact, the fate of stars is inextricably linked to the density of the universe. In a denser universe, stars may run out of fuel faster because higher gravity compresses the star, allowing fusion reactions to become more violent. And in a sparser universe, stars may live longer, but eventually die out. Scientists predict that in an infinitely expanding universe, the last stars would become so dim that the universe would enter the dark era. At that point, all that will be left in a universe will be the remains of cooled stars, black holes, and floating elementary particles. Here's another interesting thought. Why is the density of the universe so close to a critical value? This is the famous cosmological constant problem. Scientists are still trying to explain why the strength of dark energy is just right to keep the universe in a delicate balance between expansion and contraction. It has been suggested that this may have something to do with the multiverse theory, that our universe is just one of countless possible universes, and that only universes with densities close to a critical mass can give birth to observers like us. 10. Universality of the electromagnetic spectrum. When it comes to the electromagnetic spectrum, it's the workhorse of information propagation in the universe. Imagine, from the sound of the radio drifting past your ears, to the gamma-ray bursts from distant galaxies, almost all astronomical phenomena through the electromagnetic spectrum, and we chat. We human beings rely on this universal code, and slowly unlocked many secrets of the universe. Electromagnetic spectrum is actually a huge rainbow of light, from long wavelengths of radio waves, to the amazingly short gamma rays. Each wavelength has its own personality and usefulness. Let's walk through the spectrum and see how amazing it is. Let's start with radio waves, which are the longest wavelength segment of the electromagnetic spectrum. How long are radio waves? The shortest are a few millimeters, and the longest can reach thousands of kilometers. Radio waves are like trumpets in the universe, loud but low-key. What do we use it for? Kommunikation. Radio telescopes are an important tool for astronomical observations, such as the famous Arecibo radio telescope, which sadly collapsed but captured many important signals from the universe. Also, radio waves have helped us discover pulsars. These spinning neutron stars act as a natural lighthouse in space, and their radio waves flash regularly and with such precision that they could be used to calibrate an atomic clock on Earth. Further down the road is the microwave region. When you think of microwaves, you probably think of a microwave oven, but microwaves are much more useful in astronomy than a hot meal. The most famous microwave signal is the cosmic microwave background radiation, CMB. Known as the baby picture of the universe, the CMB is a record of what the universe looked like 380,000 years after the Big Bang. Imagine a sea of hot plasma at the birth of the universe. As the universe expanded and cooled, photons were finally free to travel. These photons traveled for 13.7 billion years and were finally picked up by us. Sounds like the prehistoric recordings of astronomy. Isn't that cool? Then there's infrared light. Infrared light is like the thermal imager of the universe, helping us capture warm objects like planets, atmospheres, and even dust clouds around stars. The James Webb Space Telescope, JWST, the successor to the Hubble telescope, is an expert in infrared. It has allowed us to see many previously invisible objects, such as star birth zones obscured by dust. Infrared also helps us look for the atmospheric composition of exoplanets, with chemical fingerprints like water vapor, methane, and carbon dioxide. Then we come to the visible region, which is actually a very small part of the electromagnetic spectrum, but the one we are most familiar with. This is where the light from all the stars, including the sun, is concentrated. Early astronomy relied almost entirely on visible light. By analyzing the spectrum, scientists learned for the first time that stars are made of hydrogen and helium. Imagine how amazing it is that a celestial body billions of kilometers from Earth can tell us its chemical composition from light alone. Further up the scale is ultraviolet light. The Earth's atmosphere blocks most of the ultraviolet light, so we need to send telescopes into space, like the Hubble. Ultraviolet light allows us to study young stars, hot gas clouds, and even supermassive black holes at the centers of galaxies. Ultraviolet light also reveals the secrets of high-energy processes in the universe. For example, black holes produce intense ultraviolet radiation when they engulf the material around them. By studying this radiation, we can learn about the black hole's mass and engulfment rate. Higher up, we enter the X-ray region, which is the signature of high-energy objects such as neutron stars, black holes, and supernova remnants. Earth's atmosphere also blocks X-rays, so we need to launch space telescopes. The Chandra X-ray telescope and Europe's XMM Newton telescope have helped us see the hot gas in the accretion disks of black holes. These telescopes have also found evidence of dark matter between clusters of galaxies. Finally, there are gamma rays, which are the most energetic part of the electromagnetic spectrum. Gamma-ray bursts are among the most violent explosions in the universe and can outshine even entire galaxies for short periods of time. Gamma-ray bursts can come from the collapse of a star, or they can be the result of the merger of two neutron stars. The Fermi Gamma-ray Space Telescope has captured many of these events. By studying these phenomena, scientists have learned about the behavior of energetic particles in the universe. In short, the universality of the electromagnetic spectrum allows us to peek a little through the curtain of the universe. From radio waves to gamma rays, each wavelength tells the story of the universe, and we are like a group of patient listeners who record their whispers and cries with telescopes and detectors. This is the marvelous thing about the electromagnetic spectrum, which is not only a tool of science, but also the most affectionate dialogue between human beings and the universe. Well, that's it for this installment. Kudos and comments welcome, and thanks for tuning in.